So today I'm going to talk about a workflow that my collaborators and I developed for rapid multimodal image segmentation and data extraction. And initially this was primarily used for X-ray CT images, but it turns out that the workflow can be applied to any image. So it's pretty usable. I would like to acknowledge some of my collaborators and institutions that have supported me in this, and that's the USDA ARS, Washington State University, the Advanced Light Source, the Pacific Northwest National Laboratory, and UC Davis. I particularly would like to thank Jaeming Wang, Odetta Chifoku, and Tomas Varga for all their help with the work that I'm doing. And I'd also like to acknowledge ORS Dragonfly for free use of their software. I rendered some of our data in using their software, and so you'll get to see some of those videos. So historically, segmenting X-ray CT data and images in general has often relied on thresholding. So that's separating an image into different grayscale values or different color values. And that works pretty well with simple images. So here's a single slice from an X-ray CT scan of biochar. And so you can see the biochar, the solids are light colored and the pore spaces are dark colored. And so you could just separate the histogram into light and dark areas and get a nice representation of the biochar. For more complex things, there are more modern computational methods for segmentation, including pixel clustering, edge finding, or image topography, so like watershed segmentation. But those type of things would kind of struggle with this more complex image. So this is a soil column. I'm a soil scientist. I'm going to show you lots of pictures of soils. That's what I'm into. And there's biochar actually in this soil column. And you can see that the mineral solids are light colored. They're absorbing a lot of X-rays in this image. And the voids or pore spaces are dark colored. And the biochar is somewhere in between. And it would be very hard to, say, identify the biochar in this from the voids just based on grayscale thresholding alone. And it can get even more complicated. So this is a cross-section of an almond bud. And say you wanted to identify the sepals and separate them from the actual flower primordia here. This would be very hard with thresholding, right? There's no difference in grayscale between the outside and inside of this. So you need something smarter. And it can get even more challenging. So these are X-ray CT cross-sections of plant leaves. And my collaborators are wanting to know, they want to separate the upper epidermis from the lower epidermis. They maybe want to separate a vein, which is right here, from the bundle sheath extension. And you obviously can't do this with thresholding. And watershed segmentation, other methods like that won't work. So what they often do is they go through and they hand segment these, right? They just go through an image J and kind of crop around the upper epidermis, and they'll do that for, say, 10 images in a stack, and then extrapolate information for the whole leaf from that. But it doesn't really work that well when you have thousands of images, because you can get differentiation in a Z direction in CT scans. So this is a video, this will be a video of a soil aggregate, and what you'll see is that the aggregate changes as we scan through it. Right? The volume changes, the size changes, and the components change. So in light are the minerals. We can start seeing particulate organic matter right here, right? So it comes into view and then goes away. There's other pieces of particulate organic matter that will come into view and go away. You can see them kind of moving around in here. So you can see that it's very dynamic. If you were to take any 10 images from the soil aggregate, you might not describe the whole aggregate very well. And so we needed to find a better way to deal with this type of data. And so we turned to machine learning for that, specifically convolutional neural networks. So here's an example of a neural network that's been used for object detection and instance segmentation. And it's able to identify people fairly well and bicycles fairly well. So this is a pretty sophisticated method for image segmentation. And we wanted to apply this to our CT data sets and then expand it onto basically any image data set that we came across. So for our segmentation workflow, we get our images from the instrument, and this can be a CT scanner, this could be an SEM, a TEM, it could be anything, your cell phone. And you're gonna wanna select representative images from your data set. And anytime you're trying to train a neural network, you wanna give it data that's representative of all the images that you have taken. And so you can load those into something like Fiji ImageJ, which is an open source tool developed by NIH for processing images. And you can use those to annotate your images. You can actually draw in what you want to see. And anytime we annotate our images to train a deep learning model, we want to say keep 80% for training and then hold back about 20% for testing. You always want to have an independent test set to evaluate the validity of your models. For our workflow, we developed it specifically for use in Google's Colaboratory, which is a free-to-pay cloud computing platform. But we also adapted it so that it could be used on high-performance computing systems like Tahoma. We're also adapting it right now for use on Perlmutter, one of the nurse computing platforms. Or you can use it locally. So I have a server, and I run this code on my server for image segmentation. And basically, once you've uploaded all your data to any of these platforms, you then go into the code and you input kind of the materials that you're looking for and how they're represented in your annotated data set. Right? So if you have grayscale values that you've used for annotation, you're going to put those in along with their associated material. Then you can input other model training parameters and then start generating models. And then on our platform, you can test your generated model to determine the quality of it. And then if you're happy with the quality of it, you can go ahead and apply it to all your image data and segment it and extract data from it. So this is an example of how you might go about annotating an image. So here we have 4 material classes that are represented by 4 different grayscale values. And so once you've annotated your image and you want to train a model, you would input these grayscale values into the code, and it would then be able to identify kind of what's in your image. So often what you do is say, okay, you have your object of interest, in this case a soil aggregate, and you might outline the outside of it and then get rid of the background. So we've turned that black here. And so that's just our background. Then we might go through and say, okay, well, we want to identify particulate organic matter inside of the aggregate. So we're going to go ahead and highlight that, and we're going to fill it with a light gray value. And so that's how we generate this mask right here. And then we might take our image and say, okay, well, we can segment the solids and pores pretty well with thresholding. So let's do that. So we go ahead and threshold this image, and we get these other masks. And one thing to notice is that this particulate organic matter shows up both as a solid and pores, right? And so that's where the strength of this method lies, is that we can go through and say, okay, actually what looks like solids and pores is organic matter. And so then we generate this mask right here. And this mask corresponds to this image, the reasonable representation of that image. You then take your image and mask pair, you feed it into the model trains, it validates itself. It does this iteratively. If the model improves, it will save the improved model. If it doesn't, it will go back through and try again. And you can monitor this in real time, look at your loss, and see kind of when you start getting no more improvements in the model, you can stop training then, and then evaluate your model on your test set, and then you can go through and actually take your input image, operate the model on it, and get these output masks. And so you're going to get pixel-wise predictions here. And what we use is a fully convolutional network with a ResNet 101 backbone. And the reason that we went with the FCN is it's robust to variably sized images. So a lot of our data is differently sized. We'll have different dimensions to our images, and we don't want to patch it up kind of it's important for us to use the whole images, but we might have images that are 500 by 1,000 pixels and 500 by 2,000 pixels. And a lot of other deep learning models are not robust to variably sized images. So we thought this was the best way to go. When we evaluate our model performance, I like to do a visual evaluation first. So here's an image of a leaf. We wanted to see how good a job the model did identifying the bundle sheath extension and a vein. And what we see is it did terrible, right? And so, you know, you can get these other mathematical results, accuracy, precision, recall, F1, but I think this is the most intuitive, right? You look at the model performance and say, okay, this is garbage, we got to do it again. But once you have a reasonable representation, then you can kind of select your best model based on the accuracy, precision, recall, and F1 scores that are generated during testing. And precision is just out of all the predictions that are made, how many are correct, and recall is of all possible correct predictions, how many were correctly predicted. And then the F1 score is the harmonic mean of these two. It's kind of nice to balance these two evaluation criteria. So now I'm going to kind of go into the results that we get out of this. So here's a soil aggregate that I annotated. You saw this earlier. This is actually from the test image set. So the model was not trained on this image and this hand annotated mask. And here's the computer's output. So this is what the computer thinks this aggregate should look like in like my representation. And what we see is it does a pretty good job. It's a reasonable approximation of this mask. The biggest difference is it took me about 30 minutes to make this, and it took the computer about 2/100ths of a second to make that. So it's a lot faster than I am, which is nice. And because this is CT data, right, we have thousands of these individual two-dimensional slices that we can put into 3 dimensions. And so we can do things like this. So this is a synthetic soil aggregate that a deep learning model came up with after evaluating images of a soil aggregate. And so what we can see in gray are the mineral solids, and in blue are the pores, and then in tan is actually the particulate organic matter. And this is the aggregate that you saw earlier in that fly-through video. So the piece of organic matter that had penetrated the aggregate, that's it right there. And it's actually a piece of oak. We can tell from the original images. And so now we can really kind of understand the distribution of particulate organic matter inside of soil aggregates, which is important for understanding how organic matter breaks down in aggregates, what would be CO2 fluxes out of the aggregates. We can start modeling these things that historically have been really painful to model. We can also apply this to kind of other image data sets and ask kind of more robust questions. So professionally, I work with wine grape growers and winemakers. And so here's an image of a grape seed. Sorry, set my alarm for this. So here's an image of a grape seed. And some winemakers came to us and they said, tannin extraction from grapes during winemaking is constant. So there's no decrease in tannin extraction over time. Why is that? And this has been a big question in winemaking for a long time. And it turns out that we can answer this with X-ray CT scans of grape seeds during fermentation. So here's a grape seed right here. This is late in fermentation. This is the mask that my postdoc made. And this is kind of the output. So it does a reasonable approximation of the mask that the postdoc made. And what we can do is we can look at, say, seeds over time, right? So this is pre-fermentation. This is what a seed might look like. And so we have our nucellus right here. We have some pore spaces on the outside and a little bit on the inside. And what we can see is that early in fermentation, the nucellus actually swells. So as the tannins are extracted, they're only being extracted from this outer surface right here. But over time, the nucellus actually shatters, right? And so we're actually going to start getting tannin extraction from the pores on the inside of the nucellus, which explains why the extraction rate doesn't change, right? There's a lot more surface area in the nucellus now, And that explains why the tannin extraction stays constant. And we can model this in 3 dimensions, right? So we have our integument on the outside of the grape seed. We have our pore space represented in white, and then we have the nucellus represented in this kind of peach color. And so, we can break it down into its different components and start modeling some of the things that are going on. So you can see this kind of bluish tinge on the inside. So that's a pore network model inside of the grape seed, right? And we can start looking at, quantifying the different size pores throughout the grape and get at the extraction efficiency from all the different areas inside of the grape seed. With slight modifications to the workflow, we're actually able to do instant segmentation and apply this to RGB images. So I work in ag, and my collaborators will say, oh, well, I want to know about the stemminess of intermediate wheatgrass. And so we applied this workflow to counting the stems of intermediate wheatgrass. And we can actually also get morphological traits from this, right? We can look at the area of each individual wheatgrass stem. Another colleague at UC Davis said, oh, I want to know about the morphology of grape leaves. And a challenge that they were having was their grape leaves weren't a uniform color. Normally, you might say, oh, well, let's just take, segment out the green part from this red background. Well, some of the leaves are pretty reddish. And so they were really struggling to segment this. And what we can do is, segment each individual leaf and extract individual data properties from each leaf, right? So we can get the longest axes, the shortest axes. We can even get like average color values, things like that from each individual leaf. Another colleague wanted to do something similar with hops, right? So they wanted to know about the openness of hop cones. These are used in brewing beer. And so they're looking at, they want to tie their breeding program to some of these characteristics. And so we're able to do that here. We get instant segmentation, and we can, again, extract information for each individual hop. And from that, we can look at hop openness, hop size, color, all these other attributes, which is pretty nice. So with that, CNNs provide accurate generalized models with minimal annotation and training time, and they can be applied to image segmentation problems using free resources from Google, local resources, or high-performance computing resources at national labs. If you are interested in using this, this workflow, we're currently getting it up and running on Tahoma, and it can work with basically any image data set. So feel free to contact me. My email address is devin.rippner@usda.gov. And with that, I'll take any questions.
Thank you, Devin.
Thanks.
Do you have any questions? Yes, over here, Alice. I think we have only time for one.
Thank you, wonderful talk. I'm excited about segmentation, which we used to do manually, of course. So tell me about the statistical significance. I admire your grape seed and how quickly you do these things. What do you consider before you make a hypothesis and confirmation of it? How many seeds do you think you would have to process in order to get an idea?
Good question. I think that one of the challenges is always, so these images were collected at the Advanced Light Source on Beamline 8.3.2. So getting access to that time is a challenge. In this case, we imaged 3 seeds from pre-fermentation, early fermentation, and late fermentation. And based on that small data set, we see changes in the seed morphology during fermentation. And it is statistically significant. Yeah, we've just started evaluating that. We're hoping to put a paper out this year about that. But so it's a fairly small data set. It did take my postdoc a while to annotate those seeds. But hopefully once we have this annotation library, right, we can build it out. So we can investigate things more fully once we have a collection of annotations.
Absolutely, thank you. So the imaging is the bottleneck right here, not the not
Yes.
the evaluation, right?
Yes, yeah, absolutely. In this case, for the CT scans, the imaging is the bottleneck. But for say cell phone camera images, things like that, that historically has been, it's a computational bottleneck or a person hour bottleneck.